Hi, welcome to lecture 4.2. Here we're going to talk about the principle of conservation of momentum and reflect upon a little bit about Newton's third law, a law that a lot of you will know, but is your concept right? We shall see. Okay, let's formally state the principle of conservation of momentum first. This is defined. Whenever you see conservation, it means that it is the same lah. So the total momentum of a closed system is always constant, always the same. This statement is already enough to give you 2 marks. But what does it mean to be in a closed system? Well, you could also write the more elaborated form, okay, which is the total momentum before and after a collision, because normally we talk about collisions lah, remains the same. 1 mark. Second mark, or second point, conditions, unless external force acts on it. So this is actually a continuation of Newton's first law. Okay, I'll talk more about it first, but beforehand, I'm going to show you how collision looks like. All right. So the reason why I talk about this as a continuation of Newton's first law is because in Newton's first law, right, we say that momentum doesn't change or motion doesn't change unless there's external force. So in this case, we're just rewriting this. Momentum of a system remains constant unless acted on by an external force. It's the same thing. All right, so, but the sentences will look a bit different. So let's say now I have M1 and M2, and M1 is about to hit M2. And after hitting, their velocity will change from U1 to V1 for M1 and U2 to V2 for M2, respectively. Okay, so moving on, I'm going to apply the conservation of momentum, right? And I will say the initial momentum is equal to the final momentum. Initial is before collision, final is after collision. So M1U1 plus M2U2 is M1V1 plus M2V2. What to do with the equation? Well, let us look at an example, all right, before we proceed. And I will later also apply another law here. So this is in page 4. I have ball B of mass 1.2 kilograms traveling at constant velocity, colliding head-on with a stationary ball S. So it's going to hit S. And you can see the velocity will change after... Okay, sorry about that. Don't know why it rebounded. Okay, the velocity of ball B will change after it hits ball S. In fact, ball B will rebound and travel in the opposite direction. As you can see, that the final speed is negative 0.8. But state the significance of positive and negative value for V. So this is to indicate a different direction of motion or speed of the ball. Okay? You can also say different direction of velocity of the ball. So use the graph to determine for ball B the change in momentum. So the initial speed is 4 plus 4. And the final speed, right, you can see ball B, this is B4. After ball B will go back in the opposite direction. If you look at the graph, it's negative 0.8 meter per second. So this would be delta P is mv minus mu. So the 1.2 kg, V is negative 0.8, U is 4. Hence, you will have negative 5.76. Negative. The negative just shows that the momentum is switching towards the negative direction. All these are changes. I don't even want to use the word decrease for now. It's a directional sign. Okay. So magnitude of the force acting on B. So we're going to omit the sign now because they just want the magnitude. So I'll take the change in momentum over the change in time. This is from lecture 4.1. You can see that the time taken for this momentum or the speed to drop from 4 to negative 0.8 is this section, your delta T. And the time here looks like 0.26 minus 0.18. If you're perceptive, you will also notice that we can omit the sign. All right. So this will be 72 Newton. Calculate the speed of ball S after collision. So here we can employ or use the principle of conservation of momentum. Okay, so they will hit each other, and after they hit each other, some changes will occur where the momentum will change. Okay. So I'm going to use the sum of the momentum. Initial momentum is equal to the sum of the final momentum. So M1 plus U1. M1U1 plus M2U2 is M1V1 plus M2V2. A lot of people can recite the equation. You know how to use and you know what it means. It's a totally different thing. Okay, but take some time. So here you have substituted the value of m and u and v separately. You can pause to check the substitution if you want to. And from here, you can get your v2. So you can see, right, I have diligently substituted 0 because B was not moving before the collision. So your V2 will be 1.6. So your S was not moving before the collision. So the next part, they're asking you, is this collision elastic or not? So let us move on to page 3, where I differentiate or separate what it means by elastic and inelastic collision. Okay, so I know that there's a misconception that is hanging around, or previously you might have had the idea where sticking or no sticking, that is elastic and inelastic collision. But I'm here to tell you, not really lah. Okay, that is not the real definition of elastic and inelastic collision. So I'm going to sketch out the same diagram here, M1, M2, traveling at U1, U2 before, and V1, V2 after the collision respectively. Okay, so of course, for both cases, because there's no external forces, no forces outside of the balls M1 and M2, so I can assume that the momentum is conserved, all right, for both cases. So I'm going to use sum of the initial is equal to sum of the final momentum. The sigma sign in front of P is sum, S-U-M. So here is the defining characteristic of elastic and inelastic. For elastic, energy Ke is conserved. For inelastic, Ke is not conserved. That's why I can use the Ke equation and sum up half m1 u1 square plus half m2 u2 square will be equal to half m1 v1 square plus half m2 v2 square. So the kinetic energy is not lost for elastic, but the kinetic energy is lost for inelastic. Okay? So condition for momentum to be conserved is no external force. It applies for both cases. Whereas for the second case, right, for inelastic collision, Ke is lost because there's heat, there's sound during collision. All right. And for elastic collision, we can use the relative velocity equation. So I'm going to now derive the relative velocity equation if you were to go back to page 2. Okay. So for elastic collision, the kinetic energy is conserved, meaning to say if I total out the kinetic energy before and after the collision for both of my balls, it should end up the same value. So I'm just going to plug in the equation. Okay, and I will cancel off all the halves, so I'm left with m1 u1 square minus m1 v1 square is m2 v2 square minus m2 u2 square. I am gathering all the m1 on one side and all the m2 on the other side, factorizing m1 and m2 respectively. So I see the a square minus b square inside the fraction. So now I'm going to do the same thing for conservation. Put all the m1 one side, put all the m2 one side, and factorize out the m1 and m2. So from here, by factorizing u1 square minus v1 square and v2 square minus u2 square, I get these two equations. I will just take equation 2 divide by equation 1. You can always slow down this part and check out the derivation. It shouldn't be that difficult to follow because what I'm doing is just factorizing a square minus b square, or in this case u1 square minus v1 square. So while copying this down, I noticed that most of the terms can be cancelled out, and I'm left with u1 plus v1 is equal to v2 plus u2. I'm going to rearrange. So I'll get u1 minus u2 is equal to v2 minus v1. Alright, or if I want, and normally this equation got many ways in different books, I prefer to have the prefix arranged in the same order, 1, 2, and 1, 2. So from here, if let's say you have u1 and u2, this equation will be applied if they are traveling all towards the right lah. Okay, I myself am easily confused as a human being. I would like everything to be standardized, so everything is traveling to the right. So whenever you minus 2 velocity, right, this is called the relative speed of approach. Relative speed of approach because u1 is approaching u2, and then this will be negative relative speed of separation. So we start off with 1 relative to 2. So that's why it's 1 minus 2. Okay, so this is for elastic collision only. And if any of these balls decides to travel in the opposite direction, you're going to add a negative law. We will never use sticking or travel together for elastic collision. Not allowed. All right. So momentum is always conserved for all collision because there is no external force. In this case, there's no external force. Because there are no other forces acting on the balls besides between the balls itself. So let's consider all collisions. Okay, generally sum of the momentum, initial and final, will be the same. And when it comes to all of the collisions, right, there are two types. There's the elastic, and there is the where the KE is conserved, and there's the inelastic where the KE is not conserved. Now, if the KE is not conserved, some of it will stick lah, okay? So in other words, it's a bit like a subset kind of thing. Collisions that end up sticking together is a subset of the inelastic collision. And hopefully you understand the term subset. If not, what this actually means is simply that if the collision is sticking if after colliding the two things stick together, it is inelastic, but not all inelastic will stick together. All right, it's a bit like my father has a mustache, but not all man that has mustache is my father. They'll be very stressful. Okay, so I'm just going to copy down the equation. Everything is moving to the right once again. I'll take u2 minus u1 is negative v2 minus v1. The speed of approach, because sometimes they ask you to write this in words lah, it's negative speed of separation, because v2 will travel faster than v1. If any particle is not moving to the right before or after collision, we will just add a negative sign in front of the term law. There is no equivalent equation for inelastic collision. Nada, 没有. Okay, so to find whether a collision is elastic or not, there's only one way, and that way is to find the kinetic energy. We need to be able to do some calculation to find the KE before and after the collision and compare them. So right now I'm finding the kinetic energy before collision. EK will be half mv square. I'm just going to substitute the values lah. The mass of the first ball, the smaller ball, is 1.2. Before collision is 4 square. So, and then after collision, it will be half 1.2 negative 0.8 square plus half 3.6. The bigger ball is traveling at 1.6 meter per second square. Oh, my square is missing. Hopefully I did press the square. Oh well, we shall see. If there's any mistake, I'll correct inside the notes. You can find them in the content library. Alright, so you can easily tell that the kinetic energy is not conserved because the initial and final kinetic energy is not the same. Okay, so since the kinetic energy is not conserved, meaning the KE before the collision is not the same, or specifically smaller compared to the KE after collision, the collision is inelastic. Okay, so this is how you determine. There's no other way. Please don't comment the sticky method. It is not allowed and it's not a common method. Okay, so the magnitude of the force acting on the ball here, momentum for the ball alone is not conserved because there's external force from ball S. Because you might be wondering, hey miss, actually there's a momentum leh. The force here change. Can apply conservation of momentum? Can. Consider the interaction between ball B and ball S. Okay, I find the initials very funny. So S will push B and B will push S. So force of S on B and force of B on S. So if we consider ball B alone, ball B definitely experience a force law. And this force is your 72 Newton. Because ball B have external force. Because if you take B alone, then S is external to B. Okay, but if you take the system B and S together, these two forces cancel out, so the momentum is conserved. So it depends on which system you're talking about. For B and S together, momentum conserved. For B alone, momentum is not conserved. That's why there is force, because the force from S is your external force. So the momentum here is not conserved. That's why there is a force of 72 Newton. Okay. And of course, the same thing for ball S. It will also have the same external force and its momentum is also not conserved. In fact, I think the magnitude of these two forces are the same because the change in momentum is the same, and the change in momentum is the same, and the time is the same, so the force would be the same. These two forces, same magnitude, 72, opposite direction. Sounds like Newton's third law. So let's talk about Newton's third law. So Newton's third law, it says that every force, now this one you heard many times before, it's also a Hamilton lyric. Every force acting on the body has an equal force of opposite reaction. But I'm just going to write this carefully. Every force acting on the body has a reaction force of equal magnitude, and opposite direction. So this is the easy part to write, but there are two other more hidden points, because this is acted on by the body. On the body has a reaction force, and then there's an equal and opposite magnitude by the body. And what I mean by that is, let's say we go back to your balls, two balls, let's say now we call it A and B. So if there's force of A on B, then there will be another force of A by B, or B on A lah. Okay, this is a language situation. Alright, so these are the four properties. It must be equal magnitude, opposite direction, and it also must act on different bodies. You can see right now, one of the forces is acting on A, one of the forces is acting on B, and it should be the same type of forces. So from here, right, you might be wondering, what is same type of forces? Okay, let's talk about the classic Newton's third law example, book on table. Okay, so there are two types of force. There are a few types of forces. We're going to consider four types now. One type is weight. Okay, and mg is pointing downwards. The second one is your normal contact force, N. And this normal contact force, right, happens whenever two surfaces are in contact. And the term normal means these two surfaces must be perpendicular to your contact surface. So there must be 90 degrees. This N is 90 degrees. There you go. Okay, so a lot of times, right, a common misconception, you see the normal and the contact. I'm just highlighting the name sake for you. A normal misconception is to think that N and W are action-reaction pair. But they are not. Miss, why not? The equal magnitude, the opposite direction, but they don't follow the third and fourth rule. They must act on different body. Both forces act on the book. It must be a different type, and they are different types. They are not the same type. So this is not Newton's third law action-reaction pair. The forces between the ball is an action-reaction pair because they act on ball A, one force act on ball A, one force act on ball B, and they are the same type because these are normal forces. Any kind of contact or touching force is normal force. Okay, so you might be wondering, then where is my reaction force for the book? For the normal force on the book? The book is supported by the table. So the normal force on the table on the book. But the book will also push down on the table. So this is normal force of book on table, action-reaction pair. Just like W is the pull of the earth on the book. If the earth pull the book, then the book will pull back the earth. Nani? Can meh? The book can pull the earth meh? But don't forget, the earth have a large mass. So because of this, there's no observable effect. You cannot see the effect. But this is action-reaction pair. Meaning, although the earth is pulling you down, you're also pulling the earth up towards you. Feel your power. Alright, anyway, the two other forces that's not discussed in this example, we'll talk more about this in chapter 5, are friction, which will always have to be parallel to the contact surface and opposite to the direction of motion, and tension. Tension here would be along a rope or a spring, and then it must be used for pulling. Alright, so now we're going to look at an example. Okay, so I'm going to do an example to show you what I mean by acting on different bodies, okay, by using collision. So first thing, define force. Force is defined as rate of change of momentum. Do not use F equal to ma. F equal to ma is only specially for constant mass. Alright, state Newton's third law. Since they use body A and B, I will use A and B. So you can use 1 and 2. Generally also can. Force on body A is equal in magnitude and opposite direction to the force on body B by A. It's like you push me, I'll push you back the same amount in opposite direction. Okay, both forces are the same type. So we talk about magnitude, direction, same type, and A to B and B by A. Okay, so if you want to make it more explicit, all four properties have to exist when you define. So right now you have two spheres, they are about to collide. The average force acting on sphere A is Fa during collision, and sphere B is Fb during collision. The contact time is Ta and Tb. So state the relationship. Fa is equal to negative Fb, Newton's third law, and the contact time must be the same. If you're touching me, that means I'm touching you, lor. So the time that they're touching is the same. Use your answer to show that the change in momentum in sphere A is equal in magnitude and opposite in direction to the change in momentum in sphere B. So you can use Fa is equal to negative Fb, but you know F is change in momentum over time and change in momentum of B over time B. So since Ta is equal to Tb, So you get change in momentum of A is equal to change in momentum of B. Alright, so this is what they want. The negative is the opposite direction. You can write more to explain, but it's just 1 mark, so I'm moving on. Now this graph shows you the change in momentum of sphere A and B. This is a very popular drawing. Okay, so in here you will see that your sphere A has a decrease in momentum. It has gone from 6 meter per second, 6 towards the right, I presume, positive 6, okay, to negative 3, which is to the left. Alright, the signs are all for direction. So now we are going to need to draw for sphere B, and before that I will need to talk to you about the principle of conservation of momentum. Alright, so this, whenever you see a conservation, it means that the total momentum of a system is constant unless acted on by an external force. So if you remember your first law, got force, momentum will change. No force, momentum stays the same. Okay? So conservation means everything is the same. Just like conservation of energy means total energy of a system remains constant. So conservation of momentum, total momentum of a system will remain constant unless acted on by an external force. Okay, so that's why whenever you think about first law, right, it's not as simple as, oh, things don't want to move, emergency brake, your body move forward. I mean, those are physical phenomena, but its implication is tied to the conservation of momentum. Momentum will not change if there is no external force. So conserve means no change. So right now you will have your sphere A having a decrease of negative 9. Okay, meaning there's definitely a force on A lah. But let's think about A and B together as a system. So then you will have total momentum before is equal to total momentum after the collision. So before the collision will be 6 plus negative 4, and after will be negative 3 plus PB. And you will find that your PB, or your momentum of B after collision, is 5. So your sphere B will go from negative 4 to 5. Okay? So if you just look at A alone, A decrease. If you look at B alone, B increase. Okay? So we're going to try to draw this to increase to positive 5. Now when drawing this graph, make sure that the change happen across the same time. Okay, so you can see I make sure that when the sphere A begin to decrease, sphere B will increase, and they occur simultaneously at the same time. Okay, now I'm just going to explain a bit of an extension here for you. You will notice that sphere A has decreased by a certain amount. Okay, so sphere A has dropped by, from positive 6 to negative 3. This means that the momentum of sphere A decreases by 9. So delta PA is negative 9. Alright. What about the momentum of sphere B? So sphere B would obviously have an increase. Now if you look at this, you will notice that the increase is positive 9, negative 4 to 5. So the increase is positive 9. So A decreased by 9, B increased by 9. If you take A and B together as a system, no change lor. So that's why the total momentum stay the same. Nah, plus 6 minus 4 is 10. Sorry, plus 6 minus 4 is 10. Plus 6 minus 4 is 2. Minus 3 plus 5 is also 2. So it's the same lor. That's why we have the change in momentum of B is equal to negative the change in momentum of A. Okay, so you have proven that lah. And this time that I'm marking is actually your TA or your TB, equal. Your contact time. The time where the ball touch each other, deform and separate. Okay, you might also be thinking, hey, can you actually use the graph to find FA and FB? You can if you have the value of TA and TB. here you can see that I'm trying to explain the forces that I mentioned just now. Now, when they come into contact, right, they deform a bit, and sphere A will push onto sphere B. I will link a video down below to show you that deformation in slow motion, okay? But I don't have time to crop it in. This video is very long already. Okay, so A will push on B and B will push on A. Okay, so this force, right, of course, is number one, is a normal force, so it's the same type, equal magnitude, opposite direction. So if you separate out A and B, right, A will have a force of B. You can take the change in momentum of A divided by TA. So this is what I mean by you can find the force if you have the time taken or the contact time. Okay, same thing with B. B will experience a force in the opposite direction. So if that's the case, right, you can notice that delta PA is negative. It shows a decrease, but actually it means that A will eventually change direction. Okay, A will rebound to the opposite direction because the momentum is negative. Okay, so the positive negative is more directional. As we move along, you should get a better idea.